Okay, let me just double check. Okay, cool. Everything's working now. Perfect. Fine. Okay, with that being said and all the technical issues hopefully out of the way, welcome to Chemical Confusion. This is a workshop that I concocted in the middle of the pandemic because I thought that students all across the board, whether you're really good at chemistry or not really the best at it, could really use a good refresher on the topics that actually exist today. So before we get into the details, let's just look at today's agenda. So first, a quick introduction about myself and the professors that helped, and then explaining the overall purpose of this workshop. Then we're going to go on to really realistically, three main courses in today's presentation. The first set being Chem 1405 and Chem 1411. Those two classes are kind of almost synonymous, so I really group them together because their curriculum is almost the same. And then Chem 1412, which is where we'll spend most of our time today. So with that being said, here's a little bit about me. I'm Dan. I am a tutor at the CSI Hotspot, and I'm also the president and founder of the Degenerate Orbitals here at University Park. That is our chemistry club organization, and quite honestly, we're not really the active this semester, but if anything, we're trying to get our ground running because with COVID and everything, things are getting a little complicated. That's a little bit about me. This picture on the right is about from 2019. It's been a while. I promise I don't look exactly like this. According to my friends, I've gotten a little older than that, but one can only hope. But now on to the professors that have actually helped with this workshop. A big thank you to them because they helped me reviewing content and made sure that I gave the most accurate information possible to every single person who's going to be watching this presentation today. So the first up is Dr. Pamela Auburn, a professor of Chem 1405, 2423, or 2425, or in layman's terms, in Organic 1 and Organic 2, and Dr. Jeffrey Gorman, professor of Chem 1412 at University Park as well. So the question that a lot of people are going to ask is why chemical confusion? And the reason being is because the concepts that we're going to cover today are going to be covered in interest of students who want to go into further levels of chemistry, whether you're a chemistry major, chemical engineering, you want to go pre-med, or just because you want to learn more about chemistry. That's what this workshop is for, not only to reinforce your material, but also to ensure that you have a good understanding of it for the long term. And sure, you might not be taking classes like physical chemistry, analytical chemistry, or biochemistry at University Park because we don't really offer those courses, but it's always good to have a good foundation because one thing you'll learn in organic chemistry is that everything builds up upon each other. So you have to have a good understanding of kinetics and equilibrium in order to be able to do a lot of the other further stuff you're going to be doing in organic chemistry. Same thing applies to physical and analytical. So now moving on to the actual content of today's lecture. So first, we're going to talk about 1405 and 1411 stuff here today. And the first thing we're going to really talk about is quantum theory. And with quantum theory, there are three main topics we're going to have to cover today, which is going to be electron orbitals and electron shells, and as well as quantum numbers. So when we talk about quantum theory, it's something that typically tends to faze a lot of people because whenever you think of the word quantum, you're honestly quite scared. But don't be scared. It's honestly not that bad. But for now, when we define quantum theory, we think of it as a branch of physics that explains the behavior and nature of matter and energy on an atomic and subatomic level. That's an important thing to understand here because when we think of energy in terms of chemistry, we typically think of terms such as entropy, enthalpy, and even with electrons and such as that. So when we think of energy, we think of it in quantized values. So according to quantum theory / mechanics, energy is quantized, which means that it can only exist within discrete values. Now, I'm pretty sure not every single person has taken discrete mathematics, but the idea of a discrete value is kind of like this. Whenever you play a keyboard, you can only play for notes that exist on the keyboard itself, not notes between keys. Or if you're not really a music person, think of it like stairs. So you have the top of your staircase over here, and then you have the bottom of your staircase right over here. And then to get from the top to the bottom, you have to go a step down, and another step down, and another step down, and another step down. You can only exist between the spaces that are on the steps, not necessarily in between the steps. I mean, you could try, but that's not realistically how that kind of works. So that's really how quantum theory works and the quantization of energy. So when we now talk about the first thing that we typically think of in quantum theory is about electrons and orbitals in this case. So in your introductory chemistry course, the one thing you'll typically be taught is about the types of models of atoms, whether it be plum pudding, the Bohr model, or a lot of other models. but right now we have to focus on the Bohr model of the atom because, if anything, it's strangely the most popular and for the wrong reason. So the Bohr model of the hydrogen atom is, if anything, the most easiest way to draw things because, for example, let's say we draw fluorine in this case. Fluorine is one of the halogens, and it's located in column 17. So fluorine, as we currently know it, has around 7 valence electrons. 2, 3, 4, 5, 6, 7. And as we all know with the octet rule, fluorine is going to want to have as many, trying to get its maximum 8 valence electrons in this case. But the problem is that even though we represent it exactly like that, that's not how actual orbitals and shells of electrons actually work. And let's explore as to why this actually is the case. So there are two problems with the Bohr model of the hydrogen atom, or realistically of just the atom in general. So the first one is accuracy and applicability in this case. So while it's convenient to use the Bohr model to represent electron placement, it's not accurate for atoms that are not hydrogen. This is due to other orbitals such as the p, d, and f orbital not being shaped similarly to one another. And we'll go more into that when we talk about quantum theory and such. But the idea is simply like this. Hydrogen only occupies the s orbital, and the s orbital is almost is pretty much circular shaped or spherical shaped, as you may say it. And the thing about that is that whenever you have an electron in a spherical orbital, it's pretty much just going to follow that exact path, which is kind of nice. But the problem is that's not actually how it works. So referring back to fluorine in this case, when you look at the electronic configuration of fluorine, which is actually going to be 1s2, 2s2, 2p, I believe 1, 2, 3, 4, 5, 2p5. So 1s is exactly what hydrogen exactly occupies. It's 1s1. But when you get to helium, it gets a little more complicated because you have more interactions, another electron, some neutrons in this case, and as well as another proton. And the reason that's problematic is because of something we know as Coulombic forces. So for those who haven't understood it yet, it's pretty much kind of like gravity and so the idea of a Coulombic force is you have force is equal to a constant K, charge of your first atom, charge of your second atom, divided by a radius between them squared. And the thing is, for hydrogen, it's kind of simple because you have an electron that you can use and a proton that you can use. But in this case, you actually have intermolecular forces or interatomic forces between electrons and neutrons, electrons and protons, and even electrons and electrons, protons and protons, and neutrons. So it gets a little more complicated, and that's why it's not so accurate in that instance. So now the second reason as to why is because of a principal violation. So when we look at the principal violation, it explains that the Bohr model assumes that electrons exhibit fixed orbits and trajectories when the Heisenberg uncertainty principle explicitly states that it's impossible to determine a particle's exact position and velocity at the same time. Now, this goes a little more into physical chemistry, which is the branch of chemistry where physics and chemistry just kind of collide with one another. See, we assume that with the Bohr model of the atom, that the nucleus is kind of like the sun in this case, and the electron is kind of like Earth or other planets, and it's going to simply orbit in a circular path. But again, that's not how this actually works. While our universe may do it, atoms don't necessarily do so. And that's kind of problematic because we would like to think that it's easy in order to represent these atoms in a way. But in terms of drawing it just to understand the idea of how electrons are spaced out, it's very convenient. But when you're going to say that the Bohr model is the most accurate model, that's where you tend to be incorrect because it's not accurate. Let's examine as to why. So the reason we have to do that is because we have to look at shells and orbitals in this case. So shells and orbitals typically tend to get confused, and that's also kind of being a problem here. So a shell, as we know it, is the entire shell here. So for this shell, we are in the second shell. But when we go a little more specific, we are in the subshell. So we have our S subshell and then our P subshell. But even more specifically, we can look into those orbitals. So for orbitals, S really just has it's only itself, but for P, it gets a little more interesting. So we can see here the plane, or known as R3 in math. So when we draw it out, we see that there is 2p x, 2p y, and 2p z. And that's an important thing to know because the p orbital occupies 3 important spaces. So the first one that we're going to see is the x-axis. So this will be px. The next one will be the y-axis, py. And finally, we're going to have the x-axis. Actually, this should be the x-axis. Apologies. So this should be px, and the top one should be pz. So when you look at it, it's not so spherically shaped like the s orbital is. It's much, much different. And when people tend to confuse it, that's where things start to get wrong. So when people want to go back to looking at the Bohr model of the hydrogen atom, considering fluorine has atoms in the p orbital, they're not going to be in a circle. They're going to be in the little shapes that we see here, which isn't necessarily always going to be spherical, which is a problem. Ooh, why did it do that? Okay, moving on. So now that we see that the Bohr model isn't necessarily accurate, let's dive a little more into shells and orbitals. So what distinguishes shells and orbitals besides specificity into x, y, and z components, or just an overall component of a 2, 3, 4, or 5, is quantum numbers here. So an electron shell is a collection of subshells, as we can see here, that share the same principal quantum number, n. That's important to know. But when we compare it to an electron orbital, we see that an electron orbital is a collection of electrons that share the same principal quantum number, n, angular quantum number, L, and magnetic quantum number, M. So the thing that pretty much makes these two united is the principal quantum number, n. That's all there is to it. While they may be related because they hold electrons, it becomes more specific as to the orientation and the size and shape of things. So when we go to describe quantum numbers, we have to look at it through each level. So when we talk about principal quantum number in this case, the first thing we have to talk about is the size of it. So principally, the number of the orbital is directly proportional to the size of it. So the higher the number, the bigger the size. And then when we look at angular quantum number, that describes the shape of the orbital. So with spherical, whenever we had our s orbital, that would be an n of 1. So then to find the L of that, so L is equal to n minus 1. And then when we do 1 minus 1, it's going to be equal to 0. And therefore, that's going to occupy a spherical space. And that's exactly what the s orbital is doing. But when you go to the f orbital, and when you have an n of 2, so if my n is equal to 2 here, my L is going to be 2 minus 1, which is going to be equal to 1. And therefore, I'm going to have a polar shape. And then it's going to continue going with polar, cloverleaf, and then worrying about 3 is not necessarily within the context of what you have to worry about in 1405 and 1411. Just know for L1 and L2. Oh, L0 and L1, actually. So aside from that, we also have to look at the magnetic quantum number, which determines the orientation of things. So continuing on with the previous example of n is equal to 2. So again, n is equal to 2. Therefore, L is equal to 1. And within that case right there, M is going to be any integer between negative L and positive L. So we're going to have negative 1, 0, and positive 1 for our magnetic quantum numbers if we're going to have an N of 2 and an L of 1. So that's pretty much the relationship between all the quantum numbers here. It's kind of pretty straightforward, but sometimes it can get confusing. So now that we've talked about quantum numbers and stuff, let's look at how it's actually kind of formed in this case. Referencing the numbers that are important here. In this column right here, we have the principal. And then right over here, we have our angular. And then right over here, we have our magnetic. And what we can see here is that whenever we have an M of 0, we're going to be pretty much in a spherical shape, especially with an angular. M is equal to 0. All that pretty much means, as we can refer to earlier, is that that's the orientation. So you really can't orient things if there's just 0. So positive 0, negative 0, same thing. So only one orientation there. And since L is also equal to 0 in the first column, we're going to see that's going to occupy a spherical shape, which it exactly does. But now when we move to the p orbitals, we're going to see that our L is now equal to 1, which means that's going to be in a polar shape. So that's pretty much like these little bean-like shapes that you currently see over here. So this is oriented in the z direction, this is oriented in the x direction, this is oriented in the y direction. So that's the important distinctions that have to be made here. And then as we go on, we go from px, py, pz to dz squared, dxz, dyz, dxy, dxy minus dx squared minus y squared. It gets very complicated and it looks all pretty, but for now, don't worry too much about understanding the shapes, but what you have to memorize and understand is the quantum numbers in this case. So with that, let's look at hydrogen electron orbitals in this case. So the important thing to look at this is how we actually can determine where an electron is going to be. So this equation that you're going to see on the right, a lot of it you really don't have to worry about, but the one thing that I want to bring your attention to is a little subscript here. You can't see it, but when I scroll in, it's going to be N, L, and then M. And if you remember from earlier, we talked about that being our principal number, our angular number, and then our magnetic number. Those again determine the shape, size, and orientation of your orbitals in this case. So all these numbers over here that you currently see, those are in respect to those three variables right there. So with that being said, let's analyze one of these things. Let's look at this one right over here with an n of 3. So n is equal to 3 right over here. So with the color gradient, you'll see that it's kind of fading off from a very white, almost yellowish tinge to a purple and even to black in some spaces. So in the areas of white that you see right here, those are areas in which you can find electrons. Or when we look to Schrodinger's equation, pretty much that says that the norm of psi is pretty much equal to 1 or pretty much greater than 0 in this case, which means your probability of finding an electron in that area it's 100% probable. But the thing is that in between those spaces, you see that there is some black space, which let me find a better contrasting color actually. Let's say I can use blue in this case. It's actually not blue. Let's see, I'll just try purple here. So actually that didn't blend well either. Let's just say I'm gonna use green because that's a really good contrast. In this green space right over here. So in those green spaces, we call those areas nodes. I'm gonna work with it a little better. Nodes, there's actually your psi squared or your probability of finding an electron is 0, which means there's absolutely no way you can find an electron in that space. So drawing it kind of just like in the Bohr model of the atom indicates that you can find electrons all over in specific discrete locations. That's not the case, because in some cases, there are areas where you can't find electrons, and there are areas where you can find electrons. It's all dependent on your quantum numbers in this instance right here. And that's an important thing to know when dealing with quantum numbers. So now that we've seen it in a very theoretical case, let's now look to it in a more practical. So the way we're going to look at this is through the quantum modeling of a molecule known as 12 crown 4. 12 crown 4 is a cyclic ether. So I'm going to designate that as a cyclic ether. Cyclic ether. So the reason we call 12 crown 4 is because there are 12 molecules in the ring, well, 12 atoms in the ring. So as an organic chemist, one thing you'll have to learn is learning line bond structures. And each of these little bends right over here indicate a carbon. So that's where the 12 comes from. You have 1, 2. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You have 12 main atoms in this case. And then what we also have something called implied hydrogens in this case, which are pretty much just hydrogens that are used to fill the octets of the carbons in our line bond structures. So again, remembering our rules, carbon wants to have 4 bonds because any less than that, it's not happy. Any more than that, it's also not happy. So this carbon right here is bonded to an oxygen and to another carbon. So that's going to want 2 hydrogens on this case. And that's pretty much the case for the rest of the carbons in this molecule. So let me just finish drawing this in real quick. we go. So with that drawn in, what we can see here is that this is a 2D structure of our 12 crown 4. This is a more 3D model or a quantum model of it to basically explain how we can see all the atoms and their orbitals and subshells around them. So when we look at it, we can obviously see that these little white spots right over here, those are going to be your hydrogens. So anything with a white spot attached to it is going to be a carbon. So you have a carbon here, a carbon here, let's see, a carbon here, a carbon here, carbon here, carbon here, and a carbon, I believe, that's going to be right back there. So then what's in between those carbons is going to be our oxygens. Let's see, I'm going to do a more contrasting slide. Oxygen right here, oxygen right here, oxygen right here, and oxygen right here. So 4 oxygens, exactly where we want it to be. But you'll notice something weird. There's this little spot in the middle that indicates there is some electron density within that area. And when you look at the molecule, you'll be like, wait a minute, where are the electrons? Well, they would come from the oxygens in this case, because the oxygens wouldn't want, the lone pairs on the oxygens wouldn't necessarily want to be on the outside of the ring, rather they be on the inside of the ring because of steric hindrance in this case. So when you put in all the lone pairs, you'll see that there is electron density in pretty much in a circle over here. And because of the cyclic nature of it, that's what causes the density to be kind of centralized in the middle. So that's how we can see quantum modeling be put into application of a molecule here. So even though there aren't explicitly any atoms within the center of the molecule, because of the presence of electrons, it creates a density which makes an area of electron richness, so to speak. So that's pretty much all we have for quantum theory in terms of electrons and orbitals in this case. So the key thing to remember here is that you have to memorize your rules for quantum numbers and understand that the Bohr model of the hydrogen atom is only applicable to the hydrogen atom and nothing else. Because whenever you go to the more complicated things such as helium, fluorine, chlorine, bromine, iodine, francium, cesium, that's not going to be accurate any longer. So you have to take into consideration the s, p, d, and f orbitals whenever it comes time to dealing with those. So now the next thing we're going to be touching on is periodic trends. And if anything, this is actually also really important because this tells you how the periodic table actually works in the grand scheme of things. So we're going to only focus on 4 trends today, but we see 2 extra trends. We're going to see non-metallic character and metallic character. Those aren't that important compared to the other 4 we're going to discuss today, but it's good to know that metallic character opposes non-metallic character. So we're going to focus today on atomic radius, ionization energy, electron affinity, and electronegativity. So first, we're going to start off on the idea of atomic radius. And if you've taken a geometry class or even just trigonometry, you'll know that you have a circle, and then the distance from side to side of the circle is going to be your diameter, and the half of that is going to be your radius. And in this case, that's quite literally what we're seeing here. So it's a distance between, my definition of an atomic radius is the distance between the nucleus of an atom and its valence shell. And again, looking here, we can see an accurate Bohr model of diatomic hydrogen. So in the middle, we have our singular proton here, and anywhere within the circular path, we have our singular electron. And the distance between both of them is going to be our atomic radius in this case. Or since considering these 2 are diatomic when they're bonded, it's just pretty much from this proton right over here to its outer, and same for the hydrogen on the left as well. So that's pretty much it. But the way the trend follows on the periodic table is that you start with helium, which has the smallest atomic radius. You go from right to the left, and you go from hydrogen all the way to cesium. Realistically, there should be francium and the 7th row, and then as well as your lanthanide and actinides, but I guess this picture kind of cut it out in this case. So that's the thing you have to know about atomic radius. But now let's do a little connection here. Let's connect atomic radius and quantum mechanics. So again, going back to the Bohr model, it pretty much uses a sphere with discrete boundaries. But again, that's not true because a quantum mechanical model of an atom, there is no specific distance from the nucleus in which an electron cannot be found. Because when we look back to the hydrogen model we saw earlier, all that white space is the area in which you can find an electron. It's not necessarily so quantized like we see with energy states in that case. But because of the variance of atomic radii, we need to have two specific definitions here. Now, these definitions aren't necessarily too specific to your knowledge and understanding of chemistry, but they're good to have in the back of your hand. So the first definition, which is going to be the most common definition you see, is covalent radius. So it's going to be the half the distance between adjacent identical nuclei that are connected by a chemical bond. So earlier we saw diatomic hydrogen. Now let's just say diatomic bromine in this case. So we have our first atom of bromine over here. And then we're going to have, let's see, we're going to have a bond and pretty much our next atom of bromine over here. Oh my gosh, what is this thing doing? Well, that's way too far. Sorry. I'm going to go on top here, periodic trends. Back to this. So then bromine again. So that's pretty much what we would call a covalent radius right here in the middle. And then a metallic radius is, as it kind of sounds, it's half the distance between the nuclei of two adjacent metal atoms. So let's just choose iron as a metal in this instance. So iron as a metal, and then another iron. And then here's the bond, and then the atomic radius would be from the nucleus all the way, it's half the distance between the nuclei of adjacent, so it would be pretty much like right there. Sorry, that's not so straight. Let me fix that real quick. So that's right there, and then this right here would be on the bottom would be our metallic radius in that case. So now that we've covered atomic radius, let's go to our next trend, ionization energy. So ionization energy is defined as the minimum energy required to remove an electron from an atom, which results in the creation of an ion, a chemical species with a positive or negative charge, well, realistically a net charge. So the most common occurrence you'll see in chemistry, especially in organic chemistry, is something as we call either a carbocation, which is positive, or a carbanion, which is negative. And a good way to remember this is was taught to me by my biology 1 professor, Professor Elder at UP. Shout out to him, really great professor. So when you see cation, think paw, like a cat's paw, positive. And then when you think anion, just think an, and then you see anti. So that's a correlation there. So if a carbon loses an electron, becomes a carbocation. If a carbon atom gains an electron, becomes a carbanion. And the trend on the periodic table is it starts from francium, the least, the atom, or the element with the least ionization energy, going all the way up to hydrogen, and going from hydrogen all the way to helium. So pretty much it goes like something like this if you want to combine both of them together. So that's how the trend works for ionization energy. Now we look to our next trend, electron affinity. So electron affinity is basically the energy released whenever an atom accepts an electron, in this case. So the way we can think of it is whenever a bond is broken or created. So analogous to bonding theory, so let's say we have a molecule of sodium chloride in this case. So there is a bond between that, which is technically considered an ionic bond, which we will cover in a bit. So in order to break said bond, you're going to have to put energy into said bond, right? So because of that, what's going to happen is that both of the electrons in this bond are either going to go to the chlorine or going to go to the sodium. But because this is an ionic bond and chlorine is very electronegative, which we will cover in a bit, we'll see that we're going to have sodium, it's going to have a positive charge, and chlorine is going to have a negative charge. And that's pretty much where energy comes into this case. So whenever that bond is broken, energy is put in to said thing. But whenever you create a bond, energy is released in that aspect. So whenever you form your sodium chloride again, you're going to put energy together to create the bond, and then energy is going to be released as a result of that, because the chlorine in this case is accepting ion, or sodium's electron in this case. And as you can see with the diagram in the middle, the trend goes from francium all the way up, and then from left all the way to the right towards helium. So again, it's kind of a, how would I say this, in a northwest direction from francium. So that's electron affinity. So let's now look at the relation between ionization energy and electron affinity. And buckle up because this will sound a little confusing, but trust me, it will make sense. So when we talk about ionization and electron affinity, they share the same periodic trend, but they have an inverse relationship. And the reason being is that the higher you have an ionization energy means that it will be less likely for an electron to be removed from an atom. But an increase in the electron affinity means that it is more likely for an electron to be accepted by an atom and vice versa. So let's look at it like this. Whenever you have a high ionization energy, you are less likely to give up an electron removal. But when you have a high electron affinity, you are more likely to accept an electron. So it's not so inverse in the terms of you'd think that, oh, if I have high ionization energy, I have low electron affinity. No, it's not that direct, but it's in terms of how it deals with electrons here. So if something is less willing to remove an electron from its valence shell, that means it's more willing to accept something like that. So in this example, so for now, that's all we're pretty much going to focus on. We'll come back to this in a bit. So now we have to talk about one of the most famous periodic trends, in my opinion, and that's electronegativity. So the trend, as we can see, and is pretty common, it starts with francium, goes all the way up, and then all the way from left, all the way to the right. We can see that francium is the least electronegative element on the periodic table, with fluorine being the most electronegative element on the periodic table. And this is important because when you start talking about bonding theory and such, the electronegativity difference actually plays a big difference as to what kind of bond you have. So on the right, we have a little diagram here explaining the differences in electronegativity, which determines what bonds. So between a difference of 0.0 and 0.4 in electronegativity, you will have a nonpolar covalent bond. But whenever you have a difference between 0.4 and 2.0, that's when you have a polar covalent bond. But when electronegativity tends to become very, very varying in this case, you're going to have an ionic bond, which is going to be an electronegativity difference between 2 and 4 in this case. So the difference is that in a nonpolar bond, your electrons are shared equally. In a polar covalent bond, your electrons are shared, but they're shared unevenly, with the partial negative side taking more of the electron density than the partial positive side. Versus an ionic bond, it's kind of just like stealing, right? So imagine it being like a tug of war. In a non-polar bond, you have two people of the same strength. But in a polar covalent bond, you keep two people of relatively same strength, but one is a little stronger than the other, but not too strong to take the rope from them. And then in an ionic bond, it's kind of having a tug of war between Dwayne "The Rock" Johnson and a fetus. Kind of impossible because Dwayne "The Rock" Johnson is absolutely stronger than a fetus in this instance. So now we can actually connect this electronegativity trend in terms of ionization energy and electron affinity. So let's talk about the compound sodium fluoride. So sodium in this case, we're just from all the atom just to symbolize our electrons here. So this is sodium, and it's going to have 2 electrons. We're going to have fluorine in this case. Hold on, wrong color. Fluorine in this case, and that's going to have 7 electrons in its valence shell. So we're going to have 1, 2, 3, 4, 5, 6, and 7. What's going to happen when these two bond is that of the electronegativity differences. So when we look at the electronegativity on the periodic table, sodium has an electronegativity value of 0.93, and fluorine has an electronegativity of 3.98. And remember, electronegativity is the ability for an atom to draw shared electrons, specifically those that participate in covalent bonding towards itself, which we measure on the Pauling scale from 0.7 to 0.4. So with that being said, what's going to happen here is that fluorine essentially want to take one of sodium's electrons and try and fulfill its octet right over here. So what's going to happen is that there's going to be an unequal sharing. And even though these two elements are going to be bonded together, what's going to happen is this. We have fluorine with a much bigger circle. That's an oval. Right over here. Let's move this right over here. And that's fluorine. And then what's going to happen is that the electron is going to be right over here and right over here, but it's going to be heavily skewed towards this side. So then we're still going to have the remaining 7, the remaining 6 that are remaining for fluorine, and then this 1 just for sodium in this case. And what we can see is that the difference between that, so delta En is equal to the change in between both of them. So it's 3.98 minus 0.93. And that's equivalent to, I believe, let's see, 3.05, if I can do math properly. Yeah, 05, and then therefore that's an ionic bond. And here's the thing, when we look at ionization energy and electron affinity, we know that it follows the same trend as electronegativity. So the more up you go and the more right you go, you're higher with electron affinity. Remember that fluorine is right over here, which is probably which has the highest ionization energy, the highest electron affinity, and highest electronegativity value. And sodium is right over here. So it doesn't have the worst values for either of the three, but compared to fluorine, it doesn't have the best, and it kind of doesn't win. So in this case, when we compare the ionization energy values of sodium and fluorine in this case, sodium has a lower ionization energy value compared to fluorine, which means that it's easier to remove an electron from sodium than from fluorine. And in this case, fluorine has a higher electron affinity value. It's more likely to accept an electron compared to sodium in this case. And then with electronegativity, we see that it's more like that fluorine is more likely to pull the electron from sodium, because it's right over here, towards itself, because of the higher change in electronegativity values right over there. So that's pretty much a brief summary of how these three kind of interconnect. But now let's connect electronegativity to atomic radius in this case. So atomic radius and electronegativity are both directly inverse to each other, which means that the higher your atomic radius is, the lower your electronegativity value is going to be, and vice versa as well. But they also have an inverse periodic trend. So when we look at it again with relation to fluorine, fluorine has 7 valence electrons, and it pretty much just wants to fill its shell, which means it's only 1 away from being a complete octet, which means that fluorine is not going to want to get rid of any of its electrons. But because of the fact that it only really has 1 shell in this case, it's closer to the nucleus, which means that its radius is actually pretty small. But when we compare it to the element below from it, chlorine in this case, so chlorine, so it has 1 full valence shell in the middle, and then it has so it has 1 full shell in the middle, and then next is its actual valence shell. So chlorine already has 8 electrons in its first shell, which is complete, and it's fine with that. And even though chlorine is currently pretty electronegative, but not as electronegative in comparison to fluorine in this case, the radius that it actually exhibits isn't necessarily going to be smaller, but rather it's going to be larger because it has an extra valence shell that it can have electrons be taken from. So fluorine is actually, because of its high electronegativity, means it's going to have a smaller atomic radius. And even though chlorine is very electronegative, its atomic radius is bigger than fluorine's, but its electronegativity conversely is actually decreased in that case. So when we compare it to an element like francium, which is again the least electronegative element, francium only has 1 electron in its valence shell, so it's going to have a lot more shells than this, but just so we'll call this last one out here. So we'll call this its valence shell. So it only has one electron, so that's pretty easy to steal in this case. And the distance between the nucleus of francium and its valence shell is pretty far. So chances are it probably won't even notice that it was actually stolen by another element in this case. So this pretty much covers everything we have to go for the 1405 and 1411 material. So now let's do a little quick quiz just to make sure that we have the knowledge that we have just to make sure that we understood things today. So with that being said, the first question that's asked from us is which quantum number do the electron shell and the electron orbital share? And the answer in this case, if you remember, would be n, which is a principal number. So number 2, why is the Bohr model considered to be inaccurate for all atoms except hydrogen? So the first reasoning is because of the p, d, and the f orbitals and their shapes. Second is Heisenberg uncertainty principle. Third, which periodic trend describes the ability of an atom to draw electrons towards itself? So when we look at the 4 trends we discussed today, we have atomic radius, we have ionization energy, we have electron affinity, and electronegativity. So when we think about it, atomic radius doesn't really have much to do with drawing electrons towards itself, if anything. And then when we look at ionization energy, that's pretty much the ability for that's ionization energy in a nutshell, again, is going to be the energy required to remove an electron from an atom. So that's not necessarily going to be in relationship to draw an atom towards itself. But electron affinity is also when energy when an atom accepts an electron. So again, it wouldn't be either of those 3. So realistically, our only option left would be electronegativity. And then 4th, which periodic trend does not follow the same trend on the periodic table compared to other periodic trends? So let's kind of work this one by one. For atomic radius, it went from starting at helium to left, and then from that it went up to down, and then we have ionization energy from down to up, and then left to right. And then for electron affinity, you went from down to up, and then left to right. And then electronegativity, again, as you can pretty much predict at this point, goes down to up and then left to right in this case. So the answer in this case would be atomic radius. And then finally, the next question asks us, a net positively charged atom is called a what, while a negatively charged atom is called a what? So again, from the little mnemonic we learned earlier, a positively charged atom or positively charged is going to be cation, while a negatively charged atom is going to be an anion. Remember, cat and an. Those are the biggest hints for you when you're determining those things. So if you've taken 1405 and 1411, and this is where you're stopping so far, this is where the part of the presentation doesn't become that relevant to you. But if you'd like to stay by and continue learning about some of the general chemistry 2 topics, you're more than welcome to stay by. But if you're a general chemistry 2 student, thank you for joining us. And this is where we start paying attention towards y'all now. So general chemistry 2 is a very interesting class, in my opinion, because it's harder than organic chemistry, because in this class, a lot of the concepts are very mathematically focused and not necessarily conceptually focused, which is kind of a problem because you tend to focus more on the math rather than the actual concept itself, and then you just tend to get lost in all those things. So there are four topics that have to be covered before we move to organic chemistry, but we're only going to cover three because these three have been stressed to me as the ones that students tend to when they actually take Gen Chem 2 or move on to organic chemistry 1. So these three topics we're going to cover today are going to be kinetics, equilibrium and Chatalier principle, and reaction coordinate diagrams. So moving on to kinetics. So the idea of kinetics is that you study the rate of which chemical reactions actually happen at. So in this case, we have three reactions. So we're going to have reaction A, reaction B, and reaction C. And this isn't necessarily a one-step reaction because you can see there are three layers to this. So this is the first step in the reaction, the second step in a reaction, and a third step in a reaction. We call this a multi-step reaction. And what determines multi-step reaction is the slowest step. Remember, the slowest step in a multi-step reaction is a rate determining step. So when we look at our three reactions on the right here, they're the same reaction, but each of the steps that takes it to the final product from its reactants are varying. So in reaction A, our rate determining step in this case, so RDS, as I'll call it, for reaction A, it's going to be the first one. Reaction B, it's going to be the second one. And reaction C, it's going to be the third one. Why, you may ask? Well, when you take the beaker in reaction A and put it through in reaction A, it's pooling all the water, or I guess the solvent in this case, and hindering it from going through the funnels 2 and 3 and into the Erlenmeyer flask. But when you look at B and C, you just shift the location of where that smaller funnel is, and it's just hindering the ability for the reaction to proceed at a better rate than what it could be. So now that we've talked about just like the generality of what kinetics is, let's talk about molecularity and how it relates to kinetics. So the idea of molecularity is just what you pretty much have as a reactant here. So unimolecularity, which means you only have one molecule, is you go directly from A to your products. And your rate law in this case will just be K times the concentration of A. Bimolecular is like bi, which means you have two molecules in your product or in your reactant here. You can either have two of the same molecule, or you can have one of two different molecules in this case, and they lead to the same products. But when considering the rate law, we see that it's considering for the first one, when you have two of the same product right here, so let's say rate is equal to K, concentration of A, and then concentration of A again. And that's basically A times A squared. So that's where you get the derivation for this one. And then again, for termolecular, which is something you will rarely see in Chem 1412, but sometimes your homework will make you work on it, or your professor might want you just to get some exposure to it. That's when you have three molecules. So it's either three of the two of the same molecule and one other molecule, or just three different molecules in this case. And again, same thing. You have A to the A cubed because you have A 3 times, and then A squared times B times B times C, rule the concentrations of them in this case. So that's pretty much all you need to know about molecularity. So for now, again, remember, focus mostly on bimolecularity and unimolecularity in terms of your reactions. If you're going to talk about termolecularity, just know that it exists. That's not impossible, but again, it's not that common. So now, again, Gen Chem 2 is extremely math heavy, so let's look at the mathematics of kinetics in this case. So what we can see is that there are three types of orders in this case. We have zeroth order, we have first order, and then we have second order. And in this case, they have two different rate laws. They have the differential rate law, and they have the integrated rate law. So the differential rate law pretty much just tells you the rate, or pretty much your K in this case. So your K is going to be your rate constant, and the units of your rate constant are going to be all the way down here. So for zero order, it's going to be molarity per second, and then for first order, it's going to be 1 over seconds, and then for second order, it's going to be 1 over molarity times seconds, or molarity to the inverse power times seconds to the inverse 1. And then from there, we can see two graphs. We can see a concentration versus time graph for 0th order. Pretty much, this goes pretty linearly until everything's used up. And for first order, it almost looks exponential and decreasing exponentially, which is kind of pretty much doing in this case. And then we look at the integrated rate law. This just tells you to determine the rate constant, which is what you use. So this is when you use the integrated rate law in this case. So for your 0th order, your slope is just going to be negative k. And then for your first order, your slope is going to also be negative k. And then where it starts to differ a little is that your second order, your slope is just going to be positive k in this case. Now, I'm not going to go too in depth into the specifics of how to calculate this stuff. This should have been, again, been heavily focused on in your Gen Chem 2 class. This is merely a review of the concepts, not the mathematics of it. This is just a review of the overall mathematics of how it works, not the specifics of it. And then finally looking at just like half-life. So for 0th order, it's your half-life is going to be equal to your initial concentration divided by 2 times your rate constant. For your second order, it's going to be natural log of 2 or 0.693 divided by your rate constant. And then for second order, it's going to be 1 over your rate constant times your initial concentration. So now let's start applying kinetics. And this is where it's going to be a little more relevant for students going to take organic chemistry. Just put a little star here. We're going to talk about organic chemistry here. Organic chem. So with that being said, we're going to talk about substitution reactions. So the idea of a substitution reaction is kind of like a single displacement reaction. So you have AB, or compound AB, and then molecule C. And what's going to happen is that you're going to get BC, one of them gets displaced, and then you just have A by itself, or any of the permutations that you can see fit. So there are two types. We have nucleophilic substitution that's unimolecular, and then we have bimolecular. So SN1 will be unimolecular, and it's going to be bimolecular in this case. So remember, in kinetics, what's going to happen is that when you have a multi-step reaction, your slowest step is going to be your rate determining step. And in terms for the SN1, what we can see for this specific reaction, that this step right here, or specifically the first transition state, as indicated by this little bar 1, is slower than transition state 2, less than transition state 2 in terms of speed. Therefore, that's going to be your rate determining step right here. So when we talk about substitution in a reaction right here, so what we're going to see is we're going to have something called an electrophile, which is something that wants electrons, or is an electron poor source, and a nucleophile that is a electron rich source, or and also deficient in nucleus, which is kind of what's kind of like what it's seeking. It's a nucleophile, or nucleus seeking in this case. So Rx in this case is what we call an alkyl halide. So alkyl, because you pretty much have a hydrocarbon fragment right here. So this is your alkyl group. And then the X would typically be a halogen, or it's a halide as we call it. And what's going to happen is that you're going to have an intermediate right here at transition state 1. So at transition state 1, this is C. You're going to see R, your alkyl halide, start to dissociate away from your halogen. And what's basically happening here is that the electrons in this bond are going straight towards your halogen. That's going to give you the intermediate of a positive carbocation in this case, a negative halogen, and then a negative nucleophile. So what's going to happen here is that the nucleophile will perform as something as we know as called a nucleophilic attack. It's going to attack the source that is deficient in electrons, which the nucleophile is rich in. So the halogen kind of just stays alone by itself. And then the second intermediate in this case, I got erased. The second intermediate is when the R is starting to be attached to the nucleophile, in which the electrons are essentially going to be added to the alkyl fragment right there. It's erasing. So then from there, what's going to happen is that at our end product is going to be an R attached to a nucleophile plus regular halogen that is the anion in this case. For reactions, again, it's just unimolecular here. And because it's a multi-step reaction and there are two transition states, we have to choose the slowest state. And in the slowest state, the only thing you really have reacting with itself is going to be your alkyl halide. So that will be the rate here. It's going to be K times your Rx. Now, when we look at bimolecular nucleophilic substitution in this case, let's change to, let's just say blue. Oh, blue. Let's go. Sure, let's just choose green in this case. What's happening here is that there's only one state here. So there's only one transition state. And it's what we call or really a concerted reaction, in which the nucleophile will attack your alkyl and the halide will just leave off of the nucleophile, or leave off the electrophile in that case. So it's all happening all at once. And again, since it's only a singular reaction and there's no other reactions to be going towards, that's the only step you have in your reaction. So therefore, and at that step, you have to take into consideration your Rx or your alkyl halide, as well as the concentration of your nucleophile in this case. So then that will become your rate determining step. So I'll just put RDS over here. As we can see below, the rate is going to be equal to K times the concentration of your Rx times the concentration of your nucleophile. And that's where a lot of this gets into play with kinetics and organic chemistry. Now, again, shifting away from organic chemistry because this is for Chem 1412, but it's just an application of said topic. We're now going to look at equilibrium, which is kind of very important in this course because you see a lot of equilibrium with either aqueous equilibrium, acidic equilibrium, and other things like that. So the principle that people tend to forget is Le Chatelier's principle. And Le Chatelier's principle is defined as when conditions of a system at dynamic equilibrium and a change is applied to said system, the system will respond via a shift in the direction of the reaction that will minimize the change. So think of it as you trying to essentially like, let's say you accidentally set the food you're microwaving on fire. What you're going to want to do is try to minimize the damage done. So you're going to splash water onto said thing. And hopefully you're microwaving in that case, so you don't create more of a fire, but that's a little off tangent right there. But we also have to define a dynamic equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction, which means it's an actual equilibrium with the reaction itself. So now, let's look at how K and Q are put into play here. So you may think that they're the exact same thing because the calculation is kind of the same. Because remember, whenever you calculate Q, it's going to be your concentration of your products over the concentration of your reactants. And analogously, K is calculated in the very same way. But I want you to note one thing here. Just because K and Q are calculated the exact K does not always equal Q. That's a very important distinction to make. They can equal each other, but that's not always guaranteed. So in the reaction here, when we look at the math, we have A, so we have our coefficients as our lowercase numbers, and our actual elements or compounds as our uppercase letters in this case. So again, whenever you're doing things like this, your coefficient then becomes your exponent, and then your actual thing becomes just your concentration of that. And then remember, it's products over reactants in this case. So that's something very important. So remember, Q is specifically whenever you're not, well, Q is when you're not at equilibrium. So again, not specifically whenever it's a given position in time. Q is your reaction quotient. It's a position in time when a reaction is occurring, while K is a value of Q in which it is at equilibrium. So when we talk about K, so it's at equilibrium. But also remember that there's a ton of K's we can talk about. We have K for acids, K for bases, K for water, we have KSP, we have KP, we have KC, and the list goes on and on and on, honestly. So there's a lot of distinction, but just know that K and Q, while calculated the same, are very different. So now let's actually apply the relation between K and Q here. So remember, again, K is not always going to equal Q, and that Q, in terms of calculation, is somewhat equal to K in terms of products over reactants, specifically the concentration of them. So when Q is equal to K, dynamic equilibrium, and Le Chatelier's principle says, oh, they are at dynamic equilibrium, so there's absolutely no reason that we have to shift the system to anything. So if Q is going to be equal to 0, which mathematically means that our numerator is going to 0 in this case, that means our products are kind of having a problem. So equilibrium is going to want to shift to the right in this case, rather than to the reactants. Now, let's say we have a situation in which our reactants are going to go towards infinity. And mathematically, there's a lot to consider there, but we're just not going to go too deep into that. So when K is going to be equal to infinity, we're going to have to shift more towards the left in this case, because that means there's a problem with our reactants, or whether we're taking it away, or there's an absolutely minuscule amount to the point where it's almost 0 at that point. And then, but let's say we are at some regular point where there are both numbers, but they're in varying amounts. When K is greater than Q, you're going to want to favor your products. When Q is greater than K, you're going to want to favor your products. When Q is less than K, you're going to want to favor your reactants. But inversely, at this point, whenever K is less than Q, you're going to shift to the right. Whenever K is greater than Q, you're going to shift to the left. That's pretty much the way to think about it in this point, and how K and Q are related. And remember, Le Chatelier's principle wants to do whatever it can to decrease the changes that actually exist. So now let's actually look at how change actually exists in terms of chemical reactions. So there are 3 main ways that things change: concentration of product or reactant, change in temperature, and change in pressure. That's important to know for what we're going to see next. So this is a hypothetical reaction. So the first agent of change we're going to talk about is concentration and reactant change, concentration. So in the first case, we see an increase in the product concentration. So when we increase the amount of products that we have, increase the amount of product that we have, what that's going to do is shift equilibrium to the right. But Le Chatelier's principles say, hey, I don't like that. And it's going to come in and intervene actually, and increase, thus shifting equilibrium towards the left in this case. And then conversely, what's going to happen is if you increase the reactant concentration in this case, to increase the reactant, that means equilibrium is technically shifted towards that part of the side, that part of the reaction. What's going to happen is Le Chatelier's principles say, hey, I'm going to want to go more towards the right so I can fix that, and therefore you're going to increase your therefore equilibrium is going to want to favor your reactants. So now we talked about heat in this reaction. So if we increase the temperature for a reaction, it's going to be exothermic in this case. So essentially what we're going to be doing here is favoring the right side. And that's kind of a problem because we don't necessarily want that. So what's going to happen because of Le Chatelier's principle again is that it's equilibrium to the left. And then when we decrease temperature, again, the converse of that's going to happen. So when we decrease temperature over here, what's going to happen is that it recognizes, oh no, we're losing heat. So Le Chatelier's principle is going to shift to the right. Now, in terms of pressure, the key thing for pressure is that you're only focused on moles of gas. So let's just assume that everything is gaseous. So it means A, B, C, and D are all gases. So what you're going to want to be concerned with here is the number of moles of gas you have. So on this side, we have 3 moles because 2 plus 1. And this side, we have 2 moles, which is just 1 plus 1 in this case. So if I increase my pressure, what's going to happen is that that Le Chatelier's principle is going to be like, oh no, it's going to favor the products in this case. So we're going to have to shift towards the reactants. But if I decrease my pressure because of the amount of moles, I'm going to have to shift in the other direction in this case. Now, you'll notice that I talk about a catalyst here. And the thing is, catalysts don't change anything. The only thing that, well, they change something, but in terms of equilibrium, they don't change anything because they affect the amount of reactants equally in this case. So what's going to happen is that they don't affect equilibrium. So realistically, there's not going to be a shift because of a catalyst. So again, to sum it up, catalyst does not change equilibrium. Okay, so now let's actually talk about what catalysts do. And catalysts go through this thing as we call catalysis. And the process of catalysis is basically just adding a catalyst to increase the rate of a chemical reaction by decreasing the activation energy required to produce the products from said reactants. So again, as we talked about earlier, its effects on equilibrium. While a catalyst may increase the rate of reaction, which only talks about kinetics, it does not affect the position of equilibrium as it speeds up the forward reaction and the reverse reaction. It did to the same degree here. That's all it does with equilibrium. It doesn't affect the rate at which, it only affects the rate at which the reaction happens, not whether it favors a product or in this case. And we'll look more into that when we talk about reaction coordinate diagrams. So speaking of which, that's actually our next section. So when we talk about reaction coordinate diagrams, people tend to not really understand how they actually work. And that's kind of a problem because in further classes, these will be the bread and bone of how your reaction will actually be carried out. And reactions can only be carried out if they're typically thermodynamically and kinetically favorable. And reaction coordinate diagrams will tell you whether that's the case or not. So in this very simple reaction here, we're going from product A, we'll reactant A to product B. So right over here, we have our reactant, and right over here, we have our product. And then right over here, we have our activation energy. And right over here, we just have a change in energy, which can either typically be described as like enthalpy or something like that. We'll go more into it. So now when we dissect it again, so earlier we just saw this is a one-step reaction. So in a two-step reaction, there's only one transition state, remember that. In a two-step reaction, this is transition state 1, transition state 2, and then in between your transition states, you're going to have an intermediate product. Remember the SN1 product and the SN1 reaction? We talked about how we had pretty much had an intermediate of our electrophile, which is our alkyl fragment, our halide, and then our nucleophile. So that will pretty much be our intermediate in an SN1 reaction. And then from there, we see a change in delta G, which is going to be just our change in Gibbs free energy and such. And then this is your starting product materials, and then your products. The key thing to also understand is that for the axes here, so for E, well, for the y-axis, that's the amount of energy that is required for a reaction to proceed. And then for the x-axis, reaction coordinate, or pretty much how a reaction proceeds. You can think of it as time, but it's not exactly like time. So then looking further into reaction coordinate diagrams, this one again is just a single step mechanism. So again, almost analogous to the SN2 reaction. So again, our single transition state here. So we have our reactants, which is in this case glucose and oxygen. And when you look at the products, we have CO2 and H2O, which means this is a combustion reaction. And this is where we're going to get into the discussion of catalysis and our catalysts. So what we see here is that in green, I'm going to mark, well, in green right over here, this is the activation energy required for a reaction to occur, which means this amount of energy for a reaction to actually occur. So EA over there. But whenever we add a catalyst in this case, what's going to happen is that it becomes much easier for the reaction to actually happen. So the speed is going to drastically increase, but equilibrium is not going to. So this is going to be EA, but with a catalyst. I'll just put as EAC with another subscript C in this case. So we can see it becomes much easier for a reaction to occur whenever you have less energy required to be put into this case. But it's going to be much harder and much slower for a reaction to occur when it requires more energy to be going over. And again, the delta E we see here is either Gibbs free energy, enthalpy, or just internal energy. So now we can also compare it, in this case, to endothermic and exothermic reactions. But actually, one thing I want to make a note on this is that whenever we see our delta E in this case, we'll notice is that our delta E right over here, not affected. So delta E, not affected by catalysis. And now going on to the other types of reaction coordinate diagrams here. So we have endothermic and exothermic reactions. And the way to pretty much just tell whether a reaction is going to be exothermic or endothermic is by determining the position of your reactants and your products in regards to the y-axis, which is energy. So if your energy of your reactants is going to be lower than the energy of your products, it's going to be endothermic, which means you gained energy. If it's exothermic, you're going to be losing energy, which is pretty much what we saw with almost every single one of the reactions we saw before. So delta E in this case is going to be positive. Delta E in this case is going to be negative. So now this has pretty much covered every single thing we need to cover for Gen Chem 2. And now it's the quiz time. So question 1, what is the difference between K and Q? K, again, is at equilibrium. Horrible Q. Well, Q is not at equilibrium. It's specifically at any point in time. But it specifically cannot be at equilibrium. So now the next question asks us, what is Le Chatelier's principle? And again, Le Chatelier's principle is the principle that a reaction will want to correct itself away from the direction that is shifting equilibrium. So in other words, reaction will correct itself when equilibrium is disturbed. And then now, this is going back to rate laws. What is a rate law for a 0th order reaction? So remember, when we looked at our reactant, so let's examine the three, the three rate orders in this case. So for a 1st order reaction, so for a 0th order reaction, our rate is going to be K times A to the 0 power, when we know that anything A to the 0 power is going to be 1. So it means therefore it's going to be K. When we look at 1st order, rate is going to be equal to, in this case, K times our concentration of A. So again, 0 is not dependent on concentration of reactant. And then 2nd in this case, as we learned it earlier, it's going to be K times A squared, assuming that it's same reactant, or you could just say K times A times B. So for the 0th order, it's just going to be rate is going to be equal to K. And then the fourth question asks us, what part of the reaction coordinate diagram indicates a transition state? So the various parts that we learned about, there's a lot of parts. So let's look back at the parts in this case. So right over here, where is it? So right over here, okay, we have our products, right? Well, we have our products over here, reactants right over here, and then we have our intermediate right over here, and then our transition states. So when we're going to ask ourselves, what is the answer to this question? And the answer is that this right here is called a peak. I should have probably clarified that earlier. So we'll do it now. So this is the peak. Let's see. So the part of the reaction coordinate diagram that indicates a transition state is going to be your peak. And then finally, ending our quiz today, we'll just be using Le Chatelier's principle and determining the shifts in the reaction. So we have 2A as a solid plus B as a liquid plus heat creates 3C as a gas and then D as an aqueous product. So if we increase, our stressors in this case, so when we increase the product concentration, that means equilibrium will temporarily favor the product side. What's going to happen in that case is that Le Chatelier's principle is going to want to say, hey, actually, you're going to have to shift equilibrium to the left in this case because that's how it's going to correct itself. So direction of equilibrium in this case is going to go to the left. And using the arrow notation, it's going to go more to the left and a little bit to the right. But if I increase my reactant concentration, what's going to happen here is that if I increase reactants, that means they're going to have more of the reactants in the product. So Le Chatelier's principle says we're going to have to correct that by going to the right. So arrow to the right and then arrow to the left. So when I decrease temperature in this case, so temperature is only specific really to the left. If I decrease temperature, that means I'm really hurting the left. That means I have to compensate for that by shifting equilibrium more towards the left. But if I decrease pressure, and remember, pressure is reliant on the most amount of gas molecules, and that pretty much goes towards the product side because we have 3 versus 0. So what that's essentially going to do if we decrease pressure, and that's going to hurt the right, and realistically, it's going to only shift towards the right itself. Because we don't really have a choice because left doesn't really apply to gases. And then again, remember, catalyst. What is that going to do to equilibrium? Absolutely nothing. Because remember, catalysts only affect rate, not equilibrium. And if you stayed through to the end, that's officially the end of the workshop here today. Hopefully I've been helpful in guiding you into the most important aspects of chemistry that people tend to ignore. If you would like more help in chemistry or even going through these concepts, you are more than welcome to have a session with me through Upswing or BrainFuse. And pretty much that's all I have for y'all today. Again, I really hope I've been helpful. And remember, if you do need help in any chemistry, whether it be from 1405 to 2425, we have tutors at the SLRC that are more than willing to help you with any of your chemistry problems. Oh my gosh, okay. So then from that, that's pretty much the end of my presentation. So going towards this, I'm going to stop my recording there, and yeah.